All right, in this video we're going to do some review. So we're not going to cover all these things for the first time, but we're just going to be going over to refresh your memory on these items. The first thing, basically, was dot structure. So the things to remember about that is that we're only showing the valence electrons. So we show the valence electrons. And then the only thing to remember about that is that we do one on one side before we do two together. So if we have something like carbon, all right, or if we do something like nitrogen, which has five valence electrons, we'll do 1, 2, 3, 4, and then we'll double up with the fifth. All right, next slide. So on this one, explain when an atom becomes an ion. So an ion is an atom with a charge that has gotten a charge by, it has either gained or lost electrons. Right, an electron or more than one electron. So once it has a charge, it is considered an ion. It's no longer considered an atom in the same way it's considered an ion. So a cation, right? Cation is has lost electrons, and the charge is positive. So it's lost electrons. The anion has gained, so it's negative. On our periodic table, the metals over here tend to become your cations. Your nonmetals over here tend to become your anions. All right, here we need to recognize ionization energy. You know the trends on the periodic table. So ionization energy is the energy required basically to pull electrons away from the atom. All right. When you pull the electrons away, you make them a cation or a positive ion. The ionization energy, as you move down any column, the ionization energy is decreasing. All right. And this is because as you move down, the size of the atom is getting bigger and bigger and bigger, and these electrons are negative charges, right? And the center of the atom is positive, and you have these negative charges out here away from it. And as you get further and further and further from those positive charges, it's easier and easier and easier for these electrons to get pulled away by other charges. As you move from left to right across the periodic table, the ionization energy increases. All right, and the next trend we're going to look at on here is electronegativity. Electronegativity is kind of the inverse of ionization energy. Electronegativity is the pull that a specific atom, or says how strongly one atom can pull or attract electrons. So here, fluorine has the highest ionization energy. This one has the strongest pull, and cesium and francium, which doesn't really don't really count it. Cesium has the least. Right, so it won't pull other things. So here, as we go, it's the opposite of the ionization energy. As you go left to right, it increases, and as you go top to bottom, it will decrease. All right, atomic radii, we haven't talked about this too much. an understanding of you don't need to know this, but if you do, it might help you understand the other trends, or within this explanation, I can give you something that will help you understand the other trends a little bit more. The atomic radii basically is if you have a sample of an element and you look at two atoms that are next to one another in that element, basically what you're doing is you're going from the nucleus of one element, atom in the element, to the nucleus of the neighboring atom, and you're taking this distance and you're dividing it in half. So basically it's the distance halfway in between one atom and its neighbor. And as you go down the periodic table, the atoms are clearly getting bigger. You're getting more protons, neutrons, and electrons. So as you would expect, the atomic radius increases as you go down the periodic table. But something a little strange happens as you move from left to right across the periodic table. Because as you move left to right across the periodic table, the atomic radius actually decreases. And the reason that has to do with the shielding of your non-valence electrons. What's happening as you go across here, so your valence electrons are the electrons that are in the outermost shell, and the electrons that are in the non-valence shells are still important in that they come between your positively charged nucleus and your valence electrons, right? So basically, the nucleus is positively charged, and it's holding on to these valence electrons. And in between, you can have these non-valence electrons in here shielding or blocking the pull, the positive pull on the negative charge here. So what's happening as you go across any given period is that each atom is gaining more of a positive charge. The positive charge in the nucleus is getting stronger, but you're not getting any more non-valence electrons to shield it. So you're getting a larger pull, a stronger force from the center, from the nucleus, but you're not getting any other electrons blocking the pull on these valence electrons. So what happens is that stronger pull is able to grab on and cause these valence electrons to get closer, a little bit closer to the nucleus each time, actually causing the radius to decrease as you go across a period. Ionic bonds. So ionic bonds is the force that holds two ions together. An ion is an atom that's gained a charge, right? It's gained or lost electrons to become charged. So in this case, we are talking about the attraction between positive and negative ions. On our periodic table, we have metals and nonmetals, and the ionic bonds tend to take place between, or do take place between, what are the metals over here and your nonmetals over here. And the reason for that is that the metals tend to have very low ionization energies, so it's relatively easy to take their electrons away. And the nonmetals tend to have high electronegativity, so they have the strength to just remove the electrons. So in this case, we get donations of electrons from metals to nonmetals. All right, so an ionic bond, we have, so this is the force of attraction between the ions. In this case, we can just use Lewis dot structures to illustrate what's going on with these. So with sodium chloride, this is an ionic compound. We've got a metal and a nonmetal. The sodium has 1 valence electron. The chlorine has 7 valence electrons. And it's got a very high electronegativity. And put that together with sodium's low ionization energy. And the chlorine has the ability to rip this extra electron away from the sodium, and what you end up with is then a sodium ion, right? It's got a positive charge, and a chloride ion, it has a negative charge. Now you've got this positive charge next to a negative charge ion. Opposite charges will attract, and they will bond together. So you could have the positively charged sodium next to the negatively charged ion. Now, the let's see, I'm looking ahead to our next slide. This is what we've just done, the transfer electrons when ionic bonds are formed. Now, this is also why they form crystal lattices. So when you have the positively charged sodium and the chloride ion, what will happen is that these two can stick together here, but you still have this negative charge. The whole ion is negatively charged. So you can have another chloride bond on this side, and this is negatively charged. So you can have another chloride bond over on this side. So what you end up with is you end up with this network of positively charged ions with negatively charged ions, and they form up in this repeating pattern over and over again. And this is our crystal lattice. But this is why we say it's an ionic compound, because this is what we mean by an ionic compound, because it's not a single unit. It's a big clump of ions that have formed together and formed a crystal. This, when it's in this crystal, these units, these ions, are locked tight in place. They can't move very easily. So this is why they don't conduct electricity, because you might expect that if you put a positive charge over here, you could repel some of these positive charges, but they are locked tight. They won't move. Also, if you were to disturb this in just the right way, if you were to push this one side, one row of atoms down, then you'd end up with a situation where you have this positive charge next to this positive charge, and it would just break. It would split right apart. And that's what we mean by it's brittle. Now, if we were to melt this and turn it into a liquid so hot that the positive charges could slide by one another, then it would absolutely conduct electricity. Likewise, if we were to dissolve this into a liquid, such as water, then the ions would be able to move, and these negative ions would respond to other charges. So if you have a voltage, a potential difference in charge, then the ions would be pushed and flow with it. Ionic bonds, they will take place between metals and nonmetals. So with our ionic bonds on our periodic table, again, we talked about already that they're taking place between these metals that have low ionization energies and the nonmetals that have high electronegativities. So we've got this combination of, well, it doesn't take a lot of energy to pull these electrons away, and these have a lot of strength to pull other electrons away. So you get this situation where the electrons are taken from the metals and given to the nonmetals. Recognize how the number of valence electrons in the elements that are bonding will affect the ratio of each element in the compound. All right, so what we're talking about here is if in the last example I gave you with sodium chloride, NaCl, it was a 1-to-1 ratio. But if we have magnesium and iodine, right, we've got Mg, magnesium, has 2 valence electrons. Iodine has 7. Now, iodine really wants to, is going to be more stable if it fills up, gets another electron to go in here, and it will take it from magnesium. But magnesium still isn't happy because It's gotten rid of its one of its two valence electrons, but it still has one more to go, and it's going to interact and look to give it up to another iodine atom. And so when you're combining magnesium and iodine, it's going to form in this ratio where for every magnesium ion that you're forming, you're going to need to form two iodide ions. So that's why our chemical formula for magnesium is Mgi2, because this represents that 2 to 1 ratio. Covalent bonds. Let's just break down this name for just a minute. Covalent. Here in covalent bonds, they are sharing valence electrons. So back to our periodic table. Covalent bonds take place between two nonmetals. So in this case, neither one of the elements involved is really ready to give up its valence electrons. It's still going to hold on to it. It would take a lot of energy to pull it away. So when one of the elements here, one of the atoms here, can't clearly pull the electron away from these with weak holds on their electrons, they end up sharing their electrons. And that's our covalent bond. So these take place between nonmetals. The basic illustration here is if we have hydrogen, which is a nonmetal, and another hydrogen atom, which is a nonmetal, they have this desire, they have this electronegativity, so they're going to pull other electrons in towards the gap, towards the hole that they have. But they aren't going to give away, they aren't going to let go and allow something else to just totally steal that electron. So what you end up with is you end up with this situation where you've got two hydrogen ions. There are two hydrogen atoms that are bonded together. They're not ions. This electron has filled in this gap, and this electron has filled in this gap. And now hydrogen has filled up its 1s orbital, and so it's stable. And this hydrogen has filled up its 1s orbital. It counts both of these as part of itself, so it considers itself stable and satisfied. So we have a complete unit here with the hydrogen filling in these empty spaces. Another situation is you have something like methane, CH4. Carbon has 4 valence electrons, and hydrogen has 1. So it will bond with 4 hydrogens and claim, all right, and consider those 4 electrons that the hydrogens are bringing to the table and consider those as part of its own. So you end up with a unit here where carbon has this stable octet, and each hydrogen has a stable energy level, outer energy level. Now, carbon is atomic number 6, so we have 6 protons. Hydrogen each has 1 proton. So together here, we've got the 6 protons from carbon plus 1 proton from each hydrogen. So it's got a plus 10 charge. And the electrons, we've got 8 electrons here visible, but don't forget about carbon's 1s energy level. That gives it another 2. So that means that we've got 10 protons, 10 electrons, and we formed a neutral unit, right? So whereas the ions are charged, the covalent molecules, this individual unit, is neutral, and it doesn't have a charge. And when something's neutral, it won't interact nearly as much with the things that are around it. It's those positive and negative charges that allow these things to interact. We talked a little bit about this with our trends on the periodic table. Understand when a covalent bond will form versus another bond type. So when these atoms are not willing to give up, they have very high ionization energy. It would take a lot of energy to pull the valence electrons away. So rather than being able to grab one for itself, it will end up sharing. If you have the ionic bond, you've got these with low ionization energy over here, these metals, and these with the high electronegativities. So it's able to steal and completely take the electrons from these and donate them over to the nonmetals. Talked a little bit about why the covalent bond formed the neutral molecules. The basics is that the number of protons is matching up, is the same as your number of electrons. All right, I gave you the example of methane, CH4. Another example be NH3, and this is actually ammonia. So if we take nitrogen, nitrogen has 5 valence electrons. That means it's got 3 gaps here that it's looking to fill in. And hydrogen is really good at sharing its outer electron here, so it will bond with 3 hydrogens. And nitrogen, which is atomic number 7, has 7 protons, plus the 3 protons from the 3 hydrogen, gives us a charge here of 10, right? Plus 10. And then if we count up our electrons, we've got the 7 that nitrogen brought to the table, right? And the 3 from each hydrogen. Or we could just think about, we can see 8 electrons here, plus the 1s energy level of the nitrogen. So the 8 that we can see, plus the 2 that we can't see that aren't drawn here from nitrogen's 1s, gives us a minus 10 charge. And we end up with this neutral molecule. Now, there are situations, many situations, where the electrons aren't shared evenly. The most classic example is with water, H2O. So in this molecule, we've got hydrogen, a nonmetal, and oxygen, a nonmetal, bonded together to form water. And in this case, where we have oxygen, oxygen has our 6 valence electrons. So it has 1, 2, 3, 4, 5, 6 valence electrons, and it will bond with hydrogen. So there's 1 electron from hydrogen, there's another electron from hydrogen, and oxygen now satisfies the stable octet rule. This hydrogen, its valence shell is filled, energy level is filled, and this hydrogen, it's filled. But what you end up with is oxygen is much more electronegative than the hydrogen. So the electrons are going to be pulled more towards the oxygen. And one side of this molecule over here will have what we call a partial charge. And the partial charge means that if an electron has a charge of -1, right, and neutral has a charge of 0, so that means its charge is somewhere in between 0 and -1, right? It's not as strong as an electron's charge, but yet it's not 0. It does exist. And we indicate that with the symbol here for lowercase, I believe it's a delta. Let me put a little sign here. And what this is meaning is that this side of our molecule has a partial negative charge. The hydrogen in this case is going to have a partial positive charge. So the electrons are going to spend a bit more time hanging out with the shared electrons are going to be spending a bit more time hanging out with the oxygen. And so those electrons are going to get pulled over here, and hydrogen's proton is going to be left a little bit more alone over here, and that proton that's left over here with the electrons over towards the oxygen is going to cause this side of the molecule to have a partial positive charge. And the same thing's going on between this hydrogen and the oxygen. It's getting a partial positive charge. So the proton would have a +1 charge, and so the partial positive charge would be somewhere in between here, somewhere between 0 and 1. And likewise with the partial negative charge, somewhere between -1 and 0. So it's not a full charge, but it still exists. And the neat thing that happens here with the polar molecules is that now these can interact with things around it. Now you have this little negative charge that can interact with positive charges. It can interact with other negative charges. And one of the things that it does here is it causes polar covalent molecules to have a much higher melting point. Than nonpolar. Because one water molecule can interact with another water molecule. It's got this charge it can grab onto. So if you have a neighboring water molecule over here and the hydrogen from a neighboring molecule over here, it can interact with the partial positive on this hydrogen, and it can hold on to it a little bit, right? Depending on how much thermal energy there is and how fast these are moving, it can hang on to each other strong enough to actually form a solid. And this is why water will freeze, because these molecules will slow down enough for these polar charges to hold on to each other at 0 degrees Celsius. But if you have a nonpolar molecule like CO2, carbon dioxide, right? Carbon and oxygen, it is a nonpolar. It doesn't have these partial charges. So when you have another carbon dioxide next to it, it doesn't have the positive or negative, the push or the pull to interact with one another. And what this means is that carbon dioxide, in order to turn it into a solid, in order for one molecule to lock to its neighbor, it's got to be really, really cold. There has to be very little movement of these molecules for them to actually bond with one another. And carbon dioxide, when it's frozen, is dry ice, right? And dry ice is really cold. So CO2 freezes at negative 80 degrees Celsius. So it's got a relatively low freezing point, and that's because there's not these partial charges to hold one molecule to the neighboring molecule. We went over this. The basics of a bond will be polar and nonpolar. We only need to know the very, very limited basics, and that is when the electrons are not shared evenly. So we could say the uneven sharing of electrons. And when you get into 10th grade chemistry, you'll go into a little bit more about dipole, about other things. But for us, we'll just leave it at the uneven sharing of electrons. We talked about why they have a higher melting point and how the partial charge can interact with the neighboring partial charges. Single, double, and triple covalent bonds. So this is pretty straightforward. We've been representing the bond with just by drawing two dots here. But that gets a little labor intensive. Most of the time it's actually just going to be the shared electron pair is just going to be represented with a dash. Now with something like carbon dioxide, carbon has 4 valence electrons and oxygen has 6 valence electrons. So the formula is CO2, so we know that there's 2 oxygen for each carbon. And what ends up happening here is that you'll actually get 2 pairs being shared. I'm just going to erase this little tiny mark right there in case it's confusing anyone. That was just an extra mark. So it will share these 2 pairs. And we have a very creative name when the covalent bond is sharing 2 pairs of electrons, and it's called a double bond. And we represent it with, instead of a single dash, we just use 2 dashes to represent the double bond. Something like the diatomic, right? When we say diatomic, we just mean it's a molecule with 2 of the same atoms. So N2 is a molecule that has 2 nitrogen atoms. O2 has 2 oxygen atoms. This is the way oxygen hangs out in our atmosphere as O2. It doesn't hang out by itself as just oxygen. So nitrogen has an atomic number of 7. It means it has 5 valence electrons. 1, 2, 3, 4, 5. And with another nitrogen, and it will actually share 3 pairs of electrons. And here, we've got a nice name for that. It's called a triple bond. And we represent it with 3 dashes. Covalent molecules are nonconductive because they don't have a charge. Right? Remember, voltage is a difference in charge, and when you have positive and negative charges, it can push and pull things. But if they're neutral, there's not going to be anything there to push or pull. We talked about this throughout. Basically, the ionic bond is between a metal and a nonmetal. Right? Is a metal right, plus a nonmetal. And really what's going on here is that the metal has this low ionization energy. So it doesn't take a lot of energy to pull these electrons away. And the nonmetal, you pair that up with its high electronegativity. And it will pull the electrons away. And the covalent is between a nonmetal and another nonmetal. Right? And this has a high ionization energy. And with the high ionization energy, it will not let other things pull the electrons away. So you still have the high electronegativity, so to have a big pull with the atom that it's bonding with, but if it's a nonmetal, it's not going to be able to pull it away. It's not going to be able to steal it. It's not going to donate the electron. Understand how differences in electronegativity will affect the bonds that form between atoms. We just talked about that. Understand the basic definition of metallic bonds. So with metallic bonds, you're talking about the electron C model. With our electron C model, what's happening here is if we have something like zinc, and zinc would, ordinarily we'd draw in 2 valence electrons for zinc. And zinc, the valence electrons aren't attached nearly as tightly to the metal atom. So what you end up with is you end up with really a zinc cation, right, with a 2+ charge, and somewhere close by you've got the electrons, but they're not attached nearly as tightly. So when you put that together and you have a bunch of zinc cations, right, if you have zinc, a whole sample of zinc with many, many, many atoms, you end up with this sea of these electrons around it. And they're not attached as tightly, so they'll share the electrons very generously. And the electrons are much more transient. And this basically is a metallic bond. You end up with these cations of zinc surrounded by a sea of electrons, creating a neutral unit. And this structure helps to explain many of the properties of metals because the electrons are not as tightly bound in the orbitals as in a covalent molecule. So if you were to apply a charge, these electrons could move. Also, they're not as brittle, right? If you bend this a little bit, the electrons aren't going to mind. They're not going to all of a sudden be next to a positive charge and split apart. So that makes metals more flexible. You can bend them, you can stretch them, you can do different things. And that's because these cations are being held together by this sea of electrons outside of it. So the basic thing to remember here is the term I've repeated over and over again. So you've got this electron sea or sea of electrons that surrounds metal cations. And this is because the valence electrons are not held as tightly in metals, and that's a characteristic of metals that we're not going to go into. The next thing, this causes the flexibility and the ability to shape these. So this causes it to be ductile and malleable and conductive. The transition metals generally have 2 valence electrons. just know that there are multiple ionization states for many of them, but just when you're looking at the periodic table and you've got this section in the middle, remember that you've put into the s orbital, you've got each atom as you move across here and the atomic number increases, you're adding one extra electron. And so here in the fourth energy level, you've added one to the s orbital with potassium, you've added another one with calcium. But then as you go across the periodic table here and you're adding more electrons, they're going into the d orbital. So you're not adding any more valence electrons because it's only the s and p that are the valence. So all these transition metals we generally consider to have two valence electrons, and it's these two from the s orbital, and all these are going into the d orbital. And the valence electrons, they're not as tightly bound to it. They have those low ionization energies, and they will share freely with one another. All right, that was the basic review of our material. And if you have questions, write them down, and you can review the video, and we will also talk about it in class.